Alright, we're going to talk a little bit about inclined planes now. And let us suppose we want to analyze the motion of an object sliding down an inclined plane. The only way that we can do this is to quantify all the forces that are acting on the object. So let us go about doing so. So I'm going to start off with a little bit of a drawing here. We're going to have our inclined plane at a certain angle. And we will suppose that this is at some angle, theta, and we're analyzing some object that is on this inclined plane. We must recall that the normal force is not always going to be equal and opposite of the gravitational force. So when I look at my gravitational force in this case, I see that the gravitational force is actually acting straight down from the object. So there is my force of gravity acting on the object, and we know that that is always our mass multiplied by the acceleration of gravity. We know that our normal force is actually perpendicular to the surface in which the object is in contact with. So here is my normal force here. I need to somehow get a component of this normal force. And we can do so by making this a simple geometry problem. In the opposite direction of my normal force, we actually have the negative of the normal force. We're going to call this the absolute value of Fn, and all this is the magnitude of the normal force. And we see, since we have theta here, using geometric properties, we have that our angle theta is also going to be right there in this right-angled triangle. And I notice that I have Fn, which opposite, and we have adjacent where my Fn is here. So therefore, the magnitude of Fn is equal, well, since it's a component of our gravitational force, it'll be mg cos theta. So on an inclined plane, we now know the magnitude of our normal force. What else possibly can we have acting on this? Well, we also have an applied force. Acting down the ramp. And because our applied force is acting down the ramp, we can therefore state that down the ramp is our positive direction. And the applied force is also perpendicular to the other component of our normal force. So our applied force, the magnitude of it, is actually going to be equal to mg sine theta. So we've quantified our applied force. We've got that magnitude. We have the magnitude of Fg, which is mass times gravity. We have a magnitude for our normal force. What else acts on the object as it slides down the plane? And we know also that we have the force of friction acting against the movement down the plane here. And we know that this is solved by mu k Fn, our magnitude. Well, look at this. We know our magnitude of Fn, so that means our force of friction, sorry, this should just say mu, because I haven't defined it as kinetic or static friction. So this will be mu mg cosine of theta. So we now have a way to quantify all of our forces that are acting on an object as it slides down the plane. So we now have made each of our inclined plane problems into merely a geometry problem. And I do have a few examples that I am going to go through with you to make sure that we get this understood. Messing around with my document camera. We have a frictionless plane is inclined at 10 degrees to the horizontal, and a block of mass 10 kilograms is placed on the plane. We must determine what the acceleration of the block is. So let us picture this on an inclined plane. And at 10 degrees to the horizontal, we have some block here of mass 10 kilograms, and we're going to assume that motion is going down the ramp. So we will assume in this case, yet again, down the ramp is going to be positive. So we have our applied force, we have a force of gravity acting down, and we have our normal force, which is perpendicular to the surface. And we're going to call this our positive x direction as well. We must define that. Well, if we're looking for the acceleration down the block, or down the ramp it should say, since we're looking at acceleration down the ramp, we only concerned about is our x direction. We don't need to worry about the y direction in this case. And from looking at this, we only have one object that's acting in the x direction. So therefore, my net force in the x direction is merely going to be equal to my force applied, which I know is mass times acceleration. And my applied force from the previous page, we know, is mg sine theta is my mass multiplied by the acceleration. And what do you see that's on both sides of the equal sign? M's. So they cancel out. So therefore, our problem merely becomes acceleration is 9.81 multiplied by sine of 10 degrees. Which is 1.703489. So therefore, the acceleration of the block is, I'm looking at significant digits, I only have one significant digit, so 2 meters per second squared, and the direction in this case is down the ramp. Okay. Now a second example I have for you, and I have a couple for you today just to make sure. Let us read the second example that I have written out already for you. We have a plane inclined at 20 degrees and has a coefficient of 0.10. And we must determine the acceleration of the block sliding down the plane. Let us analyze our forces yet again. And we have acceleration sliding down this inclined plane yet again. And this time we have at 20 degrees. However, in this case, our forces that are acting on this block, we do yet again have our force of gravity. We have our normal force. We have some type of applied force acting down the ramp. And we do have a force of kinetic friction acting in the other direction as my force applied. And again, my acceleration is only sliding down the ramp. Because of that, let's call down the ramp our x direction. We're choosing that, and to be positive x as well. Similar to the last example, since my acceleration is only in the x direction, I know that I only need to analyze the x components of the force. So my net force, therefore, in the x direction is going to be my applied force minus the force of kinetic friction, which will yet again, because of Newton's second law, be mass times acceleration. And we do recall that my force of kinetic friction will be mu k Fn, which is mu k mg cosine theta. And my applied force from at the very beginning will be mg sine theta because of our component and magnitude of our normal force. So let us write in what we have. Applied force mg sine theta minus mu k mg cos theta, and that's mass multiplied by acceleration. And very similar trick to the last question, each term, yet again, has a mass. So therefore, acceleration will merely be g sine theta minus mu k g cos of theta. So acceleration, therefore, is 9.81 sine 20 degrees minus 0.10 g, so 9.81 cosine of 20 degrees. And we can now merely solve for what we would get in this case. And for some reason, I don't have an answer, which is why you'll probably hear me in the background typing this into my calculator. And we get 2.4334. So the acceleration in this case of the block is, I need yet again, how many decimal places? 1 decimal place, so 3 meters per second squared. down the ramp. Okay? Now let's go to a little bit more challenging of a problem in this case. I have a 15 kilogram box resting on an inclined plane with a coefficient of static friction of 0.25, and if I raise that angle of inclination, it will remain at rest until it hits a certain angle. And at that angle, called the critical angle, the object will start to slide. So I must determine that angle theta in this case. Couple key things to make sure that we know in this case. Right now this box is motionless. So that means net force is 0. And let us look at my three-body diagram quickly right now. At that angle where it starts to raise or starts to accelerate down the ramp, this is when an applied force forces that box to slide down the ramp. And it will at the same time experience some force of static friction. Now when my box stays still, these two values are the same. I do have my force of gravity in the opposite direction, and I also do have my normal force here. So as usual, let's call down the ramp my positive x direction. And the only motion that's going to occur is down the ramp, so yet again, we're only concerned with that x direction. And when it's motionless, I have a net force of 0. So that means that my net force in the x direction will be my applied force minus my coefficient of static friction, which, when it's at rest, is 0. By setting it equal to 0 right now, we can determine that angle that it will start to lower. So that will give us mg sine theta, don't know why I put a g in there after the n of sine, minus mu s mg cos theta, and that's all equal to 0. Thankfully, because it's equal to 0, mg can cancel out in both cases. So what we have left over with is sine theta minus mu s cos theta is equal to 0. So let us do a little bit of rearranging and some playing around with this equation right now. If I were to solve for mu s, I would get mu s equals sine theta over cosine theta. I'll show that intermediate step right now here for you. That would be mu s cosine theta is equal to sine theta. Then divide by cos theta on each side of the equal sign, we get sine theta over cosine theta. Anybody who's ever taken the 4U Advanced Functions course should recognize this guy right here, the sine theta over cosine theta. Or if you're taking it right now, do not worry. If you don't know this, that's fine. I'm just telling you right now. Trig identity, this is what this is. If I ever have sine theta over cosine theta, that's automatically tan theta. So that tells me in this case that mu s is equal to tan theta. So therefore, theta is tan inverse of 0.25, which was my coefficient of static friction, and that is 14 degrees. And what this means in this case is as soon as I get an angle above 14 degrees, say 14.1, the object will start to slide. And that's all I have to say about inclined planes.